users are demanding higher and higher data rates. We've seen that for the last 30 years. For certain applications, things like virtual reality, it's very difficult to meet those using radio approaches. So for instance, if you have more than one person in a space with a radio supplied reality headset, it won't provide the performance you require. Virtual reality is an interesting application because you need very low latency, so the delay in the system must be below a certain amount. And using this approach, because of the high rates and the low latency of this fibre, free space fibre approach, offers a real solution.
So our experiment is looking at connecting two terminals together wirelessly using light. So in this case, we use fibre optic light, just like, you'd be familiar with fibre optic broadband or something like that. And effectively what we do is we send it through one of our terminals onto a mirror. That mirror can then steer our beam towards another terminal, which you can see one of them behind me here. And then that steers back into a fibre. So it's a way of us creating a virtual fibre without actually having to put a fibre optic cable in. We're investigating it because fibre infrastructure is a mature and robust technology, and it has a lot of benefits. It's high data rates, low latency communications. And that's a great advantage, but the disadvantage is that you have to have a fibre to run between, which is a physical tether, which can be a problem. So in applications where you need more mobility, ideally what you want is something like this virtual fibre setup.
Spectral resources and wireless networks are normally statically licensed between major operators such as Vodafone, EE and O2 in the UK. My research looks at how we can move away from static licensing towards dynamic licensing, where we can take advantage of underutilization of resources in wireless networks. My research considers using AI to manage fundamental resources in wireless networks. As we look to future generations of mobile technologies such as 6G, we need to try to reach certain KPIs that are specified for this new generation.
With this solution, we can bring more resilience to the radio access network and bring more flexibility and also possibly to target for energy efficient solution for the radio access network. Therefore, we can support emerging 6G applications.
We're currently using high-performance computing and ray traced simulation tools from NVIDIA to simulate large-scale wireless networks without having to deploy them in real life. I hope to find that by using reinforcement learning techniques and AI, we're able to improve the utilization of spectral resources in the network, improve the energy efficiency, and improve the throughput felt by the user.
In our latest experiment, we have been using off-the-shelf commercial devices from our industry partner Kyocera SLD Laser to build wireless communication systems that are capable of transmitting 100 gigabit per second. And that's roughly about 100 times faster than your current Wi-Fi and 5G systems you have at home. We are investigating that because of the scarcity of radio frequency spectrum. So the optical spectrum is unregulated, it's free, and it's about 3,000 times larger than the entire radio spectrum, and it provides us a wonderful resource to build future high-speed communication systems, to unlock new applications.
With this experiment, we can set up a practical system which can work for both indoor and outdoor applications. We can also take advantage of high data rate LiFi system.
My experiment is to build a test bed to test the conventional multiple access techniques we have implemented on our real life to compare to the other new technologies, which is called reshape multiple access. And the theoretical study is really rich in reshape multiple access.
Rate-splitting multiple access is a technique that we have pioneered in the past 10 years here at the Imperial College. We have now identified 40 different use cases where these techniques, rate-splitting multiple access, can be used into future 6G. And we have developed the first prototype actually to show the feasibility of these techniques. We actually working very closely with industry. Multiple industries have already contacted us. We have worked with them to show the benefit, and we hope actually that RSMA will actually convince more industries in the futures, and maybe one day be part of future 6G or 7G communications and integrated sensing.